That is one thing. And although calculation of this nonlinear coefficients are tricky, I'll explain one technique that might help you solve with relative ease. And for that, I'll take an example and demonstrate. To start, let us say I have a linear circuit, and a simple RC circuit is what I'll take. So let us say it is V in, conductance G, capacitance C. This is V out. Okay. Now, how do you find V out in this circuit? It's a linear circuit. How do you calculate V out? Yeah, voltage. I mean, let's say use KCL. That's the only thing you know. If you apply KCL here, the current flowing flowing into the capacitor is what? Yeah, let's say in time domain, what is it? Voltage is V out, capacitance is C. What is the current? C dV out by dt. So I write it as V out dot for simplicity. So that is the current. What is the current in this direction? Fine. Now you get a nice linear differential equation. If you like differential equations, you can solve it, or if you say that I don't like differential equations, I learnt in 12th standard, I like only algebraic equations, I learnt in 6th standard. You can convert it to algebraic equations. And how do you convert it? You can do Laplace transform, convert, solve, right? And you can easily solve it. It's not a big deal. So now let us say I introduce nonlinearity here. And for simplicity, I'll assume that the resistor is what is nonlinear. Okay. So if I have a linear resistor, if this is a voltage across a resistor, the current through the resistor is G times V. But now let us say I also have a second order distortion here. Okay. So this is a nonlinearity in the resistor. So let's see in presence of this what will happen. So this is V in. So this is basically G of V. V out and C. So how do you solve for this now? Yeah, I mean, once again you use KCL. So if you do KCL, I'll have the capacitor current doesn't change. The current through the resistor will be the linear portion plus G2 times V out minus V in square. Right? That's all. So now, okay, so let me ask this. So let us say now at the input I feed in a sinusoid at a frequency f0. What are the sinusoidal frequencies I'll observe at the output now? Okay, if you say only f0 to f0, so here I have 2 f0, 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 V in will also have f0. That gets squared. What do you get? 3 f0. Again, if you assume only 3 f0 is there, so once again you will have all harmonics. Okay, and in fact this you can model it like a negative feedback loop. I'll let you ponder over that. So here also I'll have all harmonics. That's what I want to make, right? So which means my output, I can write it like this. It consists of a linear term, a second order nonlinear term, a third order term, etc. Right? And you have to find everything. And if you want to find this, you have to solve this equation. This is a nonlinear differential equation. Now for linear differential equation itself is like for most of us. Now if you have nonlinear differential equation, you will just say I don't want, right? But of course we are engineers, we should not accept defeat so easily. So we, as always, we'll try and get some workarounds. So the workaround for this is the following. See, if let us say the resistor was a truly linear resistor, then we had no issues, right? We could nicely use Laplace transform. I mean, here even if you use Laplace transform, it will not help you because you'll have, convolution of Laplace, blah, 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 that will complicate it. So if this was a linear resistor, you know how to solve, right? And if this was a linear resistor, if this is the voltage across a resistor, the current is G times V. But yeah, so basically if the resistor was linear, the resistor will only generate G times V as the current. But I also need to include an additional term G2V square. So how do you think I can include that? I mean, the idea is I don't want to deal with non-linear resistor, right? I want to use it, I want to have a linear resistor alone. But if I have a linear resistor, the resistor is only generating the linear portion of the current. Right? We can assume that this is something, and then I can have an additional current source. Right? I mean, it's the same thing we have been doing for modeling noise offset, right? We'll say that our resistor is good guy, he is linear. The non-linearity is coming because of some hypothetical, current source. So this is the thing, and we'll add an extra current source now, G2V square. Fine? Seems okay? So we'll try to use this and try to solve. I'm doing some bit of hand waving, but that's okay to explain. So now I'll replace the resistor. So the circuit is now this. I have a linear resistor, and the non-linearity is generated by another current source that we are injecting in the circuit. Should be careful with the direction of the current. So this is G2 times V out minus V in square. Okay. So now we have truly linear elements. It's a linear circuit, but it has two inputs. What do? You superposition. So let us say I try to find the response only due to the voltage source first. So I have the voltage source alone, R and C. So I can find V out, right? But remember that my actual V out comprises of a linear portion V out 1, a second order nonlinear portion V out 2, a third order term V out 3, and so on. So if I solve the response due to only the voltage source, I am getting V out. But which of the components here I get from here? The linear term. Is that okay? I mean, again, simple thing to see is if I apply a sinusoid at F0, what will be the sinusoid I'll find in output? So which means you are getting only the linear portion here. Is that okay? So this will give me the linear portion of this. Fine. So this is the first part. Now second part is where things are going to be interesting. So if this V in is giving the linear portion, all the nonlinear terms must be coming due to the response of the, from the response due to the current source. Is that okay? So I found the response due to the voltage source, so I'll now neglect it. I'll zero it. I'll now inject the other input, G2 times. Huh?
Do you switch off the dependent current sources during?
We'll come to that. Hold on. Now assume that V out. Now that's where I'm coming at, right? So here this is a signal here. I know what is V in, but I don't know what is V out, right? If I exactly know what is V out, I can do it, right? Basically, if I know V out, this entire thing I can substitute here and find it. Then it will be correct. But unfortunately, you don't know V out fully. In fact, our goal was to find V out. Now it looks like to find V out, we need to know V out before. So it looks like we are going in a loop. So can you suggest a way in which we can get out of the loop? It won't be accurate, but some reasonable approximation. I'm sorry? Right, that seems like, it's not like we don't know anything about V out, right? We know something about V out. This is the linear portion. So what we can assume is my V out is approximately only the linear term, right? This I can do as long as my linear term is greater than the second order nonlinear term, this in turn greater than the third order term, and so on. And if you have a scenario like this, we call this as weak nonlinearity. We have nonlinearity, but they are not so strong that they are overpowering the linear portion. Okay. So now I'll replace my V out with V out 1. So it is no longer a unknown thing; it is a known quantity. Right. So if I find this, what will be the I mean again now it's a linear circuit. You know what is this guy? You know R and C. We can find V out. But which of the components here I'll get from this? Again, the simple way to understand is, let's assume that V in is a tau naught F naught. V out 1 is the linear portion that will also contain a tau naught F naught. So what is the source here? What is the frequency the source has? 2 F naught. Okay. So V out will have 2 F naught component. So which of the components I am getting here? The second order nonlinearity. Okay. So here if I find V out, that will give me this is okay. So now I found V out 2. What do I do next? Yeah, I mean, see, remember that in this case, let me copy this. See, in this case, I actually had to know what is V out, but at that time I knew only V out 1, but I know V out 2 also. So now I will approximate V out as both. So which means my current should be G2 times V out 1 plus V out 2, right? So if you expand it, I'll write it directly. I'll have V out 1 minus V in square plus 2 times G2 minus V in times V out 2 plus I'll have G2 times V out 2 square. Okay, is okay. Now I've already found the response due to the first guy in the previous step. Now my goal is I need to find V out 3. Which of these two terms will give me the third order nonlinearity? Second term, right? Because this is basically linear portion, contains tau naught only F naught. This contains a tau naught 2 F naught. That will give me 3 F naught, right? Whereas this guy will give me the fourth order term. So if you want to find only the third order term, I will say that V out 2 only has V out 2, right? Simple thing is look at the powers, right? That's why I wrote it like this. So here it's V out 1 times V out 2, that gives V out 3, loosely speaking, right? So I'll only take this as my excitation now. So basically here the injected current will be 2G2 times V out 1 minus V in times V out 2. If I do that, I'll once again find what is V out in this case, and that will give me, what will that give me? V out 3. So I'll find this, and then you can keep repeating it. So the idea is you start with the linear term. From the linear term you get the second order term. From here you get the third order. From here you get the fourth order, and so on. And typically with the first 3-4 terms you are set, because it's a weak nonlinearity. The first 3-4 terms will exactly capture the nonlinearity for the most part. So although, I mean, this is just an approximate thing, this is the best thing you can do, right? Because otherwise you'll have to go and solve this nonlinear differential equation. That is a nightmare. Instead, what you do, see, this is basically something that we always do. If you don't know how to solve a problem, reduce it to something that you can solve and then solve it. That's all. So we took the nonlinear circuit, converted to a linear circuit by assuming that the nonlinear terms are an extra current that is getting injected. So again you start with nothing and you get the linear portion. Now we put the linear portion here, that will give me the second order term. Now we use the second order term and get the third order term, and so on. That logic okay? So this method is called method of nonlinear currents or method of current injection. So you'll have some time, so let me actually do an example so that you get the hang of this. And as an example, I'll consider the negative feedback thing. Same thing. Correct.
So why are you writing V?
Where am I writing? Oh no, that is because this source itself has V in, right? I mean, basically, don't assume that this is some voltage you are applying. This is the other signal that you are applying. This other signal also has V in component. Okay. So let's take this negative feedback. Let me just solve this quickly. I'm going to do it. So let's assume that okay, let us say this is V in, V out. This is VE. So this guy gives me alpha 1 VE plus, let us say, alpha 2 VE square and alpha 3 VE cube. Only 3 terms let's consider. So again, our goal is to find the effective nonlinear terms at the output, right? So let us use this current injection method and see how we can quickly solve this. So again, the first step is you take this nonlinear guy and assume that it's linear. So I'll assume that this is only a linear block with again alpha 1. So which means the remaining terms must come from another input. Okay. I'll assume that we are having another input. Let us say that is some xi. Okay. Now again, you know what is VE, or first let's write V out. I know V out is going to be some k1 times this. Sorry, it's a linear term plus second order nonlinear term, so on. And my error signal, what is my error signal? V in minus beta V out, right? Let's have it like that. So again, the first step, again, now it's a linear system. Let's not consider this input. We'll only consider V in and find what is V out. So which means for the first step, I'll assume that my xi is 0. Right? That is the injected signal here is not there. Oops. This is 0. So I'll find V out. What is V out? Alpha 1 by 1 plus alpha 1 beta V in. So this is my linear term V out 1, right? Let me directly write it here. Fine. This much is straightforward. So now I'll start computing the nonlinear terms. So again, for finding the nonlinear terms, input is shorted. So let me short the input. Okay. So the xi I have to add is this. So let me write it here. Where do I write it? Xi is alpha 2 V square plus alpha 3 V cube, right? And I have found only V out 1 now. My goal is to find V out 2 next. Okay. So let me write V here. V is V in minus beta times V out. Now the only information I know about V out is V out 1. So I'll write it this way: alpha 1 V in so what does it simplify to? It's V in by 1 plus alpha 1 beta. Okay. So my injected signal is basically alpha 2 V square plus alpha 3 V cube. Now my goal is to find the second order nonlinear term, right? So in these two, which term will give me the second order nonlinear term? V square. Okay. So only to find V out 2, I have to consider only V square. Simple. So my xi right now I'll make it to be equal to alpha 2 V square. So which means it's alpha 2 V in square by 1 plus alpha 1 beta whole square. This is my VE. This is alpha 2 V square. I'm not considering this term because right now I want to find only the second order nonlinear term. We'll go step by step. So this, as of now, it's ignored and we are doing it. So now it's simple. I need to find the transfer function from this point to the output. What is that? If I apply an input here, how much of it appears at the output? Yeah, why do you say that? Can compute it, but okay, let me do it. So let us say I apply an input here. What is the transfer function from this input to the output? Alpha 1 by 1 plus alpha 1 beta. Everyone knows. So basically the transfer function from this point to the output is alpha 1 by 1 plus alpha 1 beta. Now I'm looking at the transfer function from here. What should I do? See, what I'm saying is, from here to the output, it's alpha 1 by 1 plus alpha 1 beta. From here to here, what should it be? I have to divide it by alpha 1. So it's 1 by 1 plus alpha 1 beta. I mean, you can compute it, but I'm just giving a straight reason, right? So my output now is the second order term, that is my injected signal by 1 plus alpha 1 beta. I know my injected signal, let me write it. It's alpha 2 v in square. So I'll have 1 plus alpha 1 beta. Right? So now you see you got it straight away. You don't have to see what is x plus y plus z whole square. In your previous calculation, anyways I'll make you work out in assignment so that you revise a plus b plus c whole square formula. So here you have this square, so you have to see which terms come and stuff. It will be slightly messy. But here you see, I mean, like, we got it in one shot. So let's also compute quickly V out 3 and we'll wrap up. Hopefully we have time. Let's see. Let me erase this. So now I'm interested to find V out 3. So let me, let me write it V out 2. V out 2 is alpha 2 v in square by 1 plus alpha 1 beta whole cube. So once again, for let me do it here. Right now V out 2 is known. So now my error signal VE, I can update my error signal because now I know V out 2 also. So this is already there. Let me make some space. So in addition to this, I'll have minus beta V out 2. Fine. So V out 2 will directly replace alpha 2 v in square. Okay. Fine. Now I am interested to find the third order term. Now look at my error signal. So this guy is getting squared. So if I square this, which term will contribute to third order nonlinearity? If I square this thing, I get the cross term that will generate the thing. So that is basically minus 2 beta alpha 2 v in cube by 1 plus alpha 1 beta whole power 4. So from here, this is the third order term I'll get. Similarly, I have alpha 3 v cube. If I cube this guy, what will be the third order term? If I cube this, only this term will give me the third order term. So I'll have v in cube by 1 plus alpha 1 beta whole cube. Right? So I know xi. Now I can find v out 3. What is v out 3? The transfer function from this point to the output. It's 1 by 1 plus alpha 1 beta. So this entire term will get divided by things. So let me write it and finish it. Plus v in cube. This will be whole power 5 whole power 4. Is okay? Again, if you want to find the fourth order term, you can go and do it, but we'll stop with this. So the idea is this. So you start by assuming that your thing is purely linear first, and that the nonlinear terms are added as an extra signal. So that gives you the linear portion, and using the linear portion, you update the input to the nonlinear block. So, and from there you find v out 2, and for v out 2 you take only the term that gives you the second order nonlinearity. In this case, that was this alpha 2 v square. So that with that I approximate my error signal, and that gives the injected signal, and you find what is v out 2. That gives the second order term. Now for third order term, you do the same thing. Now you know an additional information about v out. You update this error signal or the input to the nonlinear block. So you know the input to the nonlinear block is the earlier one minus an additional term now. Now that is processed by the nonlinearity. You consider only those terms that give you the third order term, and that is basically this, and then you find the transfer function from that to the output, and that's V out. Right? So this is a nice trick you can use if you have to find nonlinearity. So yeah, I'll stop here. Let's continue.